Welcome to The Explainer. You know that feeling, right? You watch just one video on something totally new and bam, your entire feed is suddenly all about it. Well, today we're diving deep into the incredible tech that makes that happen, a system engineered to learn your tastes almost instantly.
So what is the secret here? How on earth can an app seem to read your mind? Well, I can tell you, it's not magic. It's all about speed. Specifically, it's about how insanely fast the system can learn from what you just did and then retrain itself.
All right, here's our game plan. We're going to start with the core problem of real-time learning and the two absolute monster hurdles involved. Then we'll get to the solution, a system called Monolith. We'll see how it works, check out its real-world performance, and then wrap it all up with what this means for the future of our feeds. Okay, so at its very core, the goal for any modern feed is to get smarter using your most recent actions. That video you just liked, the creator you just followed, that single fresh interaction, it is by far the most valuable piece of data for predicting what you'll want to see next.
But, trying to do this for hundreds of millions of people all at once creates two enormous engineering problems. To make real-time learning actually possible at a global scale, you have to solve both of them.
And these hurdles, they really boil down to two things, a problem of size and a problem of speed. On one hand, you've got this constantly expanding universe of users and content, and on the other, our tastes and trends are changing in the blink of an eye. Let's tackle that size problem first. Engineers call it sparsity and dynamism. Just try to imagine a giant spreadsheet with a row for every single user and a column for every piece of content. It would be unimaginably huge, and it would be growing every single second. There's no way it could fit on one computer. So, to manage this colossal amount of data, a lot of systems use a kind of shortcut called hashing. But there's a huge risk. If it's not done perfectly, two different users or videos can accidentally get the same ID number. That's a hash collision. The analogy here is perfect. It's like a coat check attendant giving the same ticket number to two different people. It just creates chaos and makes the recommendations way worse.
Now for the speed problem, which has an even cooler name, concept drift. This is just the simple fact that our interests are not set in stone. The source paper for this puts it perfectly. A user interested in one topic could shift their zeal every next minute. What you were totally obsessed with yesterday might be old news today.
And what that means is any system that's trained on old data, even data from just a day ago, is always playing catch-up. It's like trying to guess what your friend wants for lunch based on what they liked back in high school. It's just not going to work. To have any chance of being right, the system has to learn from what is happening right now. So, you've got this problem of massive size and a problem of incredible speed. How do you solve both at the same time? Well, this brings us to Monolith, a system designed by engineers at ByteDance to do exactly that. Monolith tackles these problems with two key innovations. First, something they call a collisionless embedding table. It's a super clever way to store data without any mix-ups. And second, a real-time online training architecture that lets the system learn on the fly. So how does this whole thing actually work? Let's pop the hood and take a look at the mechanics that give Monolith its power. First up, to solve those data collisions, Monolith uses a special data structure called a cuckoo hash map. And it's named after the cuckoo bird because if a new piece of data needs a spot that's already taken, it can literally kick out the old data to another one of its potential homes. This simple but brilliant process makes sure every single item gets its own unique spot, which totally eliminates those damaging collisions. But of course, a collision-free table could get gigantic. So, to keep things manageable, Monolith is also really smart about what data it holds onto. First, it filters out rare data that doesn't really help with predictions. Then, it puts an expiration date on old information. So, if a user goes inactive, their data is automatically cleared out to make space for new stuff. Now for Monolith's second superpower, real-time learning. It's all built around something called a streaming engine. Just think of it like a pipeline. When you interact with the app, your data flows into this system, which has two paths it can take to learn from it. One slow path and one very fast one.
Now, most older systems use what's called batch training. That's the slow path. They collect data for hours, sometimes even days, and then train the model in one big chunk. Monolith can do that too, but its real power, its secret sauce, comes from online training, the fast path, which processes your feedback almost instantly.
And that fast path is the absolute game changer. This online training creates this incredibly high-speed feedback loop. A user's action can update the model in minutes, not hours or days. This is how the system adapts to that concept drift, almost as it's happening.
Okay, the design is super impressive, I get it. But does it actually perform any better? Let's look at the results from the experiments the team ran to prove it.
First things first, they had to prove their core assumption. Do those data mix-ups, those hash collisions we talked about, do they actually hurt the model's accuracy? Does it really matter? Well, the results were definitive. The team compared the accuracy over time between a standard system that had collisions and Monolith's collision-free system. And in every single test, the collision-free model was significantly more accurate. It proved that keeping your data clean isn't just some small detail, it's a huge deal. Next, they ran a live A/B test on a production advertising model, putting the new real-time training up against the old batch method. And the improvement was just massive. As you can see from the data here, the online model performed between 14 and 18% better every single day for a week straight. So, after this deep dive into such a powerful real-time system, what are the big takeaways? What does this all tell us about where our feeds are headed? I think there are 3 really crucial lessons here. First, clean data matters a lot. Avoiding collisions is absolutely essential for accuracy. Second, real-time learning isn't just a small improvement, it's a massive leap over training on old data. And finally, this whole thing proves that with smart engineering, it's actually possible to build systems that can handle incredible scale with both power and grace. You know, this kind of real-time learning isn't science fiction anymore. It is already in our pockets, and it's shaping what we see every single day. And that leaves us with a fascinating question. If our feeds can learn from us in a minute, what will our digital world look like when they can learn from us in a second?